So in order to get prepared for this exam, as I said, you need to review soil compaction, introduction to foundations, shallow foundations, and deep foundations notes. Compaction. Compaction is the removal of air from a soil sample, and consolidation is removal of water from the pores in a soil sample. What are parameters affecting level of compaction, moisture content? When we start adding moisture to a soil sample, it will have a positive effect on achieving a higher level of compaction. But at a certain point, or when we pass the saturation point, then adding more water will have a negative impact on the level of compaction. So that's why that's important for us to find the optimum water content or moisture content that yields the maximum dry unit weight, which is basically the highest level of compaction. Other than moisture, compaction force, or basically the equipment that is used, and type of soil, if it's well graded or poorly graded, or if we have too much fines or clay, these will all impact compaction of a soil. So for compaction, this was the last lab, and we went over the standard Proctor compaction test, which uses a hammer with a weight of 5.5, and then the hammer is dropped on a soil sample from 12 inches. And you had to compact soil in the mold in 3 layers, 25 number of drops per layer. The objective of this test is to find the optimum water content that yields the maximum dry unit weight. The important formulas for compaction are these two. So this is moist unit weight of soil. We have total weight of soil divided by total volume of soil. This is weight of compacted soil, and this is volume of compacted soil. And then using moist unit weight and water content, we can actually calculate dry unit weight of soil. So for example, if we have the result from one trial of a compaction test, then we can calculate dry unit weight. We used a mold, compacted soil in this mold. Weight of mold and compacted soil is 11.4 pound, and mold when it's empty is 5 pound. So weight of compacted soil is 11.4 minus 5 pound. This is a standard mold, so we know volume of this mold, which is equal to volume of soil, is 1/30 of a cubic feet. So we can calculate moist unit weight as weight of compacted soil divided by volume of compacted soil. This is in pound, this is in cubic feet. Our moist unit weight is 192 pounds per cubic feet. And then we can calculate dry unit weight using the formula that dry unit weight is equal to moist unit weight divided by 1 plus water content. So it's 192 divided moisture content is 9%. 1.09, which gives us 176 pounds per cubic feet. We also talked about field compaction, soil type, moisture content, and compaction factor, such as thickness of leaf, intensity of pressure applied by compacting equipment, and the area over which the pressure is applied are important factors. We also reviewed a couple of rollers that are used for soil compaction: a smooth wheel roller, ship foot, pneumatic, vibratory, and dynamic compaction. So make sure that you review those slides and understand which type of roller is suitable for which type of soil. I also showed you a simple formula that you can use to calculate the amount of soil compacted per hour in cubic yard. In order to calculate that, you need width of the compaction, speed of the equipment, thickness of compacted leaf in inch, and number of passes. We also use 16.3 in the formula to convert different units to cubic yard. After you do the calculation, you also need to consider job efficiency factor. So we cannot achieve the 100% of that number. Based on the job efficiency factor, we may be able to get 90% of that, 83% of that, or 75% of that. For example, calculate the compacted cubic yard per hour if compactor width of 6 feet, a speed of 7 miles per hour, thickness of leaf 8 inches, and test strip indicates 4 passes are required. This is when job efficiency is 100%, but if job condition is described as normal or average, then you need to multiply that number by 83%, and this is actually what we will achieve. We also went over this example to calculate which one of these is the most cost-effective option to do an embankment fill with a total volume of 8,500 cubic feet and a void ratio of 0.7. So using these two formulas, again, the total volume of the embankment fill is 8,500, void ratio of 0.7. We rearrange this formula and calculate volume of void as 0.7 times volume of solids, and then use this to replace volume of void here. Then we have volume of S plus 0.7 volume of S is equal to 8,500, and from there you can calculate volume of solids. So we need to bring volume of solids of 5,000 cubic feet from each one of these borrow pits. So for example, if we look at borrow pit A, we need volume of S is 5,000 cubic feet, it has a void ratio, which is volume of void divided by volume of solids of 1.08. So volume of void is 1.08 times volume of solids, which is 5,000. So we get our volume of void as 5,400 cubic feet. Add these two together to have the total volume, and then multiply that number by cost per cubic feet to have the total cost. And then we need to do the same thing for B, C, and D, and then compare costs to find the most cost-effective option. Lecture number 7, we talked about soil field tests and reports, different types of boring, how many core boring are required, how deep do we need to continue. We also talked about different types of field tests that are performed to evaluate bearing capacity. The tests that we talked about included a standard penetration test, or SPT, which is when we have a rod and a weight trying to push a split spoon sampler into the soil in 3 increments, each one 6 inches. And N value is the number of drops or blows required for the last 12-inch penetration. The other one was CPT, which is a rod that has a cone at the tip, and then that rod is pushed into the soil continuously, and it measures resistance at the tip and skin friction resistance. Then we also talked about dynamic cone penetration, which is a handheld device. You can perform it. It's less expensive and it's easier to perform, but it's not as accurate as SPT or CPT. And then I also talked about vane shear test, which can be used to measure C, or shear strength, or cohesion of clay. Make sure review the pros and cons of SPT and CPT. And then we talked about foundations. What is the difference between shallow and deep foundation? Different types of shallow and deep foundation. So based on the construction method, we have driven piles and bored piles. And whenever we have limitation with respect to regular piles, we can use micro piles. Then we went over examples of calculating the ultimate bearing capacity for shallow foundation using Terzaghi's formula, where the ultimate bearing capacity is coming from the strength because of the cohesion between the particles, surcharge, and weight of soil. So these are the 3 main formulas. There is no groundwater in the vicinity, so you can use the formula based on the shape of foundation, a strip, a square, or circular. This is width of foundation, and this is depth of foundation. And in this case, Q is moist unit weight of soil times depth of foundation. Make sure that you have access to the bearing capacity factors table. Use the friction angle provided in the question to find the correct bearing capacity factors for your question. Then we also talked about the cases where we have groundwater table close to the shallow foundation. Case 1 is when groundwater table is above the bottom of footing. So when that's the case, instead of moist unit weight, you need to use effective unit weight. This is moist unit weight. Now we need to use effective unit weight. And that is saturated unit weight minus unit weight of water. And unit weight of water is 62.4 pound per cubic feet. So in the formula, instead of gamma, you need to use gamma prime. Instead of moist unit weight, you need to use effective unit weight. And that again is saturated unit weight minus unit weight of water. Then when there is no water, we said that surcharge is gamma dF. But in case 1, where groundwater table is above the bottom of footing, Q is gamma times H plus gamma prime times D. This is our groundwater table. Above groundwater table, we have moist unit weight, and this distance is H. Below groundwater table, we have gamma saturated, and this is what is important for us, from groundwater table to bottom of footing. So that's D and H. So the modified equation to calculate Q is gamma times H plus gamma prime times D. Case 2 is when groundwater table coincides with the bottom of footing. In this case, Q doesn't change. Q is gamma dF. But you need to use gamma prime, which is gamma saturated minus gamma W. Case 3 is when groundwater table is below the bottom of footing. So Q doesn't change. Q is gamma dF. Gamma, you need to look at how far the groundwater table is from the bottom of footing. If D is more than width of foundation, then you can just use gamma. If D is less than width of foundation, then you need to use gamma average. We also talked about settlement in foundation. We have uniform settlement or differential settlement. And a total settlement is when we have the settlement right after the structure load is applied, which we call it immediate or elastic settlement. And if we have fine-grained soil with clay, we have the removal of water from the soil, and that is consolidation settlement. So remember, for your questions, you need to use a settlement of 1 inch. And if the question is asking you to find the required minimum width of foundation, based on settlement limitation, then you need to use this formula. In order to find the actual bearing capacity and settlement of a shallow foundation, we can do a test that is called plate load test, which basically we have a plate. This is width of plate. Then use a hydraulic jack to apply load. Measure load per area and settlement. Then when we have the results, QU of plate and settlement of plate, we can use formulas to find QU of footing, actual footing, and settlement of footing. So you need to make sure that you are selecting the correct formula. If you're looking for ultimate bearing capacity, the formula for clay, QU of footing, is actually equal to QU of plate. In sandy soil, QU of footing is equal to QU of plate times width of footing divided by width of plate. And if it's talking about settlement, then in clay you need to use this formula, and in sandy soil you need to use this formula. Our last lecture was about deep foundation. We can have steel piles, concrete, precast or cast in place, timber piles, and composite piles. Make sure that you review the slides on pros and cons of each of these materials for pile construction. Then we went over different types of equipment that is used for pile driving. And then we talked about how to calculate ultimate bearing force in a pile. So we said that the ultimate bearing force is the total of skin friction force and end or point force. Check your gradebook. Let me know if you have any questions or concerns with any of the grades that you see in your gradebook. Extra credit points are not added. I will add them to your final grade after we're done with the third exam. But you can check your gradebook. Under extra credit total, you should see a number out of 3. And I will add that to your final grade. Okay. Good luck with your exam, and let me know if you have any questions.